welcome to lecture 2. So all of those things that seemed like magic last lecture that were not explained well enough, finally we can go through them very slowly. Okay, so let's get started with all that. I have a lot to get through today, but it won't be too horrible, I don't think. So the chapters of our textbook, Dive into Systems, relevant to what we're going to talk about today are chapters 3 and then chapters 6 and 9. So please skim chapter 3 in addition to 0, 1, and 2 like I said before. You don't have to, there's no real time limit, as fast as you humanly can, but you don't have to pay too much attention, just skim. The first chapters I want you to read, though, are chapters 6 and 9, and those, I do believe, have to do with assembly, so I can confirm that right now, but those are the important ones. Boop. Yeah, so we got, C and then assembly, both of those. So, yeah, there's no real rush to these, like, I'm not going to test you on these readings, but the more you read, the faster you'll understand things, and I'm going to give you a programming assignment today too, and it will just go much cleaner. Alright, so I've shown you assembly already. I've shown you a bunch of things. I've shown you move, SVC, stuff like that. ARM, the people at ARM, they have documentation for all of these assembly instructions. So like here's a page for general instructions, such as these, and then there's another page for data transfer instructions, stuff that have to do with memory. So if you look at both of these, just scroll down like, oh, where's move? And I'll show you all the different things you can do with move, which is crazy. So there's this one. The move instructions, like, all right, here you can do stuff with W's, you can do stuff with X's, which is what we've done. All right. So there's more to it. And if you look through these, you'll get some good information sometimes. It's useful. So just keep that there. You know where these links are now. And so let's talk about those magical things called registers, which I haven't really told you enough about yet. I just showed you how to put stuff in a register before, and I went a little too fast, right? Just to get a first program out the door. But let's take our time now. Okay, so what in the world is a register? We put some values in there, at least. We know it's something that can hold a value. So every CPU has some, essentially what are global variables that live inside of it, all right? They're things that everybody can access, and they're very fast to access. You can get them very quickly because they're right there on the CPU. All right, so it's like if the CPU had its own little personal memory. All right, those are called registers. They're very fast to access. So here's the CPU, and among other things, like it has the brain there, it has a way to execute instructions. It also has a bunch of registers. It has a good chunk of them, so you can hold stuff for later. Okay, they're like little temporary variables. And if we have, and we do, we have a 64-bit CPU, that means, what the meaning of 64-bit means that every register is able to hold 64 bits of data. That's one of the key features of a n-bit CPU. It can hold that many things, that many bits in each register. So there are also 32-bit CPUs, and that means each register in a 32-bit CPU can only hold 32 bits of data, and that used to be the norm. Now we've moved onwards and upwards to 64-bit stuff. All right. So one thing I like to do in most of my lectures, we didn't have time for them last time, but I like to give little exercises where you pause the video and you try things. And so at Clovis, our mascot is the Crush, and we're about to have an in-class exercise abbreviated as ICE. So of course, our in-class exercises will be called crushed ices. So here is an exercise for you to ponder on your own. All right. Ask for help if you need it. But yeah, if this were like a in-person class, I'd ask you to work with other people. But please, maybe you guys can set up viewing parties if you'd like, and you can help each other on these crushed ices. But here's my question for you. All right. So every instruction, ARM64 instructions, are 32 bits long. So every instruction, like you say move something, like let's look at what we had last time. Lecture 1. Return in assembly.s. So like here's an instruction, move, some moves, SVC 0. Each of those instructions take up 32 bits. That's just how it works. They're encoded in 32 bits. Okay. So like if we said move W0 55, like we did that. Move W0, the number 55, like secretly somehow that's getting, like, it's 32 bits long. It's encoded that somehow, okay? I claim that 5 bits are being used to specify which register you're putting stuff in, like RD. It's like destination register. It's between bits 0 and 4. That's 5 bits total. So 5 bits are being used in this move instruction for saying which register we want to move into, all right? So if you have 5 bits of room to say which register you want, how many registers must there be then? All right, think about that. If you have 5 bits that you can encode which register you want to talk about with, 5 bits, five blanks, how many registers are there? Must there be? Did you figure it out? So let's think about this. So the smallest register, the lowest number that's 5 bits long, is the number 0. So in binary, right, you have 5 slots to fill. You can fill them with zeros or ones. So like this is the number 0 in decimal, right? You have 1, right? That's the next one. That's the number 1 in decimal, all the way to a bunch of ones, right? 5 ones. 1, 2, 3, 4, 5 in binary. That is equivalent to the number 31 in decimal, isn't it? So that means if you maxed out the space, and you might as well, there should be 32 registers that you can talk about inside of the CPU. Otherwise, why use 5 bits? Does that make sense? So therefore, that's 32 total. And a quick way to get at that answer is, all right, I have 5 blanks, and I can put 2 things in each blank to the 5th power. Pretty cool, huh? So there are, in fact, 31-ish registers. There's a couple special ones that we don't really get to use. And here's like a picture if we zoom in. So I'm calling these general purpose registers because there are other registers. There's other special variables inside the CPU that do other fancy things. All right, but these are ones we can like put numbers in and do addition on. They're called the general purpose registers, and they are X0 through X30. All right, so that's only 31. Okay, that's only 31 registers. I promise there is a 32nd one, and it's depending on the instruction. So here are the general purpose registers. You got X0 through X30. Also W0 through W30. I'll show you in a second that they're the same thing. All right, so X0 through X7 are these, X8 does something, X9 through X15 does something, and then you go all the way to 30. Some of these have special names, LR, FP, blah, blah, blah. So that's 31 registers. Where's the 32nd? All right, there is a special register called the 0 register. That's like your 32nd register sometimes. That holds always the number 0. Which is kind of interesting to think about, like a register where you can always access the number 0. All right, so that kind of counts as the 32nd one, let's say. So there really are 32 registers, okay? And there are also special other ones over here that we will get into later, some of them, okay? So they're just places inside the CPU where you can hold stuff, okay? SP, for example, that's a fun one. That's called the stack pointer. Where is that? That's a special register. The stack pointer shows where the stack is, because like if you're calling functions, you have to know like where is the top of that. And SP, that register, holds the address of the top of the stack, which is nice. So it remembers that. It's like a little variable. It's like a little pointer. All right. What's another good one? LR also has to do with registers and where to return to. PC, that's a very important one. And that's actually not a register that's general purpose. PC, if we zoom in here, PC is another special register. You never have access to it, but it's secretly there. It's called the program counter. That's a special register. It holds a secret number that is the address of the current instruction we're trying to execute. So like here's the CPU. Among other things, we had our SP, right? Here's SP. You can think of it as like, it's essentially that, right? There's another one called PC. So one register sitting inside the CPU is called PC. There are others. And PC points to, it's a pointer to the current instructions, the address of the current instruction memory. So here's memory. It's like, all right, PC is pointing to, maybe I should draw it like this. Here's memory. PC is pointing to this address in the memory table. And so like you go look up there, get the 32 bits, right? Because every instruction is 32 bits long. It's like, all right, sitting there, that's like our move instruction. That's like move into W042, blah, blah, blah. Does that make sense? So PC is pointing to, because in memory is where instructions live as well, it's pointing to the 32 bits that make up this particular instruction that it's currently trying to execute. That's called the program counter, right? So there are some color-coded things here, but for now, just use X0 through X28 all you want without any extra thought. It doesn't really matter. Try to stick to the smaller numbers, though, when you're doing an assignment. It'll save you later. But eventually, X19 through X28, these guys will be special, and we'll care about them in a special way. But not until we learn how to make functions in assembly do we care about those. These two guys, don't touch them until I teach you how to touch them, okay? Honestly, we can get by just using LR instead of, and not FP ever, but stuff for later. We'll talk about it, okay? So those are registers. They're just special variables inside the CPU, okay? And also, like I said, X's and W's, we use them separately here. So move into W0, move into X8. They're really the same thing. They're talking about the same register. So let's talk about that. Every W register is just the lower 32 bits of the corresponding X register. So touching a W register or an X register messes with the other one, usually. All right. So W registers are 32-bit halves of things. Like if you ask for, like I like to put stuff into, what do? We did W0, right? So W0, if this is W0, you can put stuff there. You can put 42 there, but it's really part of a bigger register. It's part of X0. It's the lower 32 bits of X0. You see that? That's kind of the idea. This is all of X0. That's what's going on. Maybe I should draw this slightly differently. 42, and then X0, the whole thing, has more room over here for other stuff. If you want to put a 64-bit value, but the lower 32 bits, that's the W. All right. So let's see here. The reason we use W, like the reason we do that instead of just putting the number in the X register instead of the W one, is because we like to pass ints a lot of the time. Like we only care about 32 bits a lot of the time when we're programming. Ints in every language are 32 bits long. All right. So there's no use going to 64-bit land and using 64 bits to hold stuff, because you actually are using more space than like anybody could ever access. Ints can only be 32 bits, so you must use the W part if you're talking about ints. And so exit codes, for example, are 32 bits, like main returns an int, yeah? So you can only talk about the 32-bit portions of that, and so that's why we use W registers, right? They're just the rightmost 32 bits, so that we can talk about ints, okay? And yeah, X registers would just be too big otherwise. So that's kind of what every X register looks like. Like the whole thing is the X register, like X5, X17. And then this bit, W5, W17, it's the rightmost 32 bits, okay? So writing to one messes with the other. They will clobber each other. That's the technical term, okay? So just keep that in mind when you're writing assembly. Don't talk about both X0 and W0, because one messes with the other, okay? So that's what I wanted to say there. And now let's do some simple assembly. Let's talk about it together. Let's do some arithmetic in assembly, and I also want to teach you the debugger if you've never learned that before, GDB. It's very, very useful. All right, so let's make a program. We don't have any way to print anything yet, so let's make a program that calculates this answer. Let's learn how to do math in assembly, and let's put the answer in, let's say X4. And then to view it, we could like make it the exit code if we wanted to, or something like that. But let's make this happen. So let me pull up my notes. Let's make an assembly program that does this math. Okay. So I'll make a new file. I will. Let's see. I'm in my lecture 2 folder. I'll make a file called arithmetic1.s, because I'll have more of these. And so, again, there's some boilerplate that we need in every assembly program. We say .global _start, and that's just saying, all right, I'm about to define a place in my program. It's called a label _start. That's where the program begins. And I have to tell the assembler, the thing that's going to make object code out of this, it's a global label, look for it. All right, anybody can see it. Start is a global label. It's not just for me. It's like public versus private. Global kind of means public in a sense. And so, okay. Let's do all these things. So I'll teach you all the assembly instructions, but first we need these numbers in places. So let's put like in, let's use X registers for everything. Let's do X0 holds 87. Let's put 87 in X0. Let's put 25 in X1. This can be, I don't know, X5 for the number 2, X2 and X3 for these guys. And let's start with that. Let's put all these numbers in those places. So to put a number in a register, you say move. All right. Those are called immediate values. We're going to put in the instruction itself the number that we want to move. All right. So we're going to move an immediate value into a register. So a hard-coded number, that's an immediate value. Okay. I'm immediately giving it, essentially. So move instructions look like this for your X register, your destination X register. That's why you'll see that shorthand when you look at the documentation pages. Saying this essentially does this as if it were C++. Okay, so let's move 87 into X0. So move into X0 the number 87. You got to put the number sign. It's very important. Okay, and so we're saying X0 equals 87. That's what's going on there. I hope that makes a little bit of sense. Do I want to use X registers? Because eventually I'm going to use, let's see. Like I want to show you the answer, essentially. So maybe, because return codes have to be 32 bits long, let's use W registers instead, actually. I think that would be a little bit better. Let's use W0, W1. I had a method here, so let's do W0, W1, W5, W2, W3. Okay, so this is all the same. You'll see in the documentation, instead of XD, you'll see WD. Not a big deal. But you can only put 32 bits now. All right, so let's say instead of X0, let's do W0. So it's the 32 bits, 32-bit half of X0. Let's do that. And then let's do the same for W1, 25. Move into W1, the number 25. And then I'll do the same for all the other ones. Let's get 2, 7, and 3 in W5, W2, W3. 2, 3, 5. So this will be the number 2, 7, and 3. There. So now all the numbers are in the registers. All right. And then let's do some math. Okay. So to do math, there's an add instruction, there's a sub instruction, there's a mul instruction, and then there's two kinds of division instructions. We'll get to that. All right, so let's do every bit first. Let's do this addition on W0 and W1, and let's store it into W6. So the way you do it is you say add. You say the two things you want to add. I want to add the things in W0 and W1, the 87 and 25. So they're in W0, W1. And then where do I want to put it? I want to put the answer in W6, please. All right. And so that goes at the start, actually. It's kind of like a C++ line. I'll show you in a second. So that's how you do it. You say add into W6, summing up 0 and 1, W0 and W1. Okay, so that's essentially this line. The reason it's kind of backwards is it's supposed to be reminiscent of this idea. W6 equals, like an assignment statement, W0 plus W1. That's essentially what it's doing. Does that make sense? And so, okay, we have that. Let's then, all right, we have that answer in W6. Let's multiply it by W5 and store that answer in W4. So let's take this multiplication on W6 and W5 and store it into W4 with a mul instruction with the same kind of syntax. So we'll do, all right, let's mul, put the answer into W4. I'm going to multiply W6, which is that addition result, with W5, that 2. All right. So again, what this just did is it put into W4, what it will do, it's an assembly instruction for taking and placing into W4 the result of multiplying W6 and W5. They're just little scratch registers for us. All right, so I got that answer. I can't divide just yet because I don't know what to divide. I have to compute the 4, right? I have to compute the 4 by doing the subtraction. So let's do that subtraction. And you don't have to give a different register. You can do the subtraction on W2 and W3 and place the result in one of those. Let's just like place the result. Let's reuse W2. That's fine. It's okay with that. So we can do sub for subtraction, place the result into W2, and compute the answer by taking the old W2 and the old W3. So we're replacing W2. W2 equals W2 plus W3. It's fine with that. Okay. And then, W2 minus W3, excuse me. And then we want to do division. We want to do division. We have two options. We can do sdiv or udiv, and that's signed division or unsigned division. And so you do sdiv, signed division, when you might have negatives. All right, if you want to do negative values and divide by those, you have to do signed division so that it understands those things. Because you're putting ones and zeros in registers. It's not sure, like, is this a number that's negative, or is it just a really big normal number? Okay, because we encode, right? We encode numbers that are negative with very large, like with the 31st bit set to a 1. In intland, at least. Hopefully we were remembering that a little bit. So yeah, unsigned versus signed, we have to tell the CPU which one we're using. It doesn't know. It can't assume. Okay, so we're just using nothing but positive numbers. Our result's going to be a positive number, so we can do unsigned division. Okay, there's no real difference for us. That's that idea. So we can say udiv for unsigned division. No negatives anywhere. And let's, so we're going to divide W4 and W2 for sure. But where do we want to put the answer? W question mark. What should we put here? What do we want to do? Let's say, I don't know. Answer in W4. Okay, that was my answer. Cool. So let's overwrite W4. And we'll do it like this. W4 equals W4 divided by W2 using unsigned division. Okay? And so yeah, that's that. For a lot of these, add, sub, mul, I think just add and sub, honestly. Mul and div probably don't work like this. Definitely for add and sub, you don't actually have to put a lot of these things in registers. You could have done something like this. You could have said, instead of putting W25 and W1, like the last bit, the second number that you give to add, could have been an immediate value like this. You don't have to put everything in a register. So that's something that you could have done. Okay. Mul, I'm not sure. Sub should work. Udiv also, I'm pretty sure does not work. Div for sure needs everything in registers for certain reasons. Okay. And then also division by 0, for some weird reason, it returns 0. It gives back 0 because there's no concept at the assembly level of like throwing an exception or anything. It's like, all right, I'm just messing with register values. I'm going to give you some sort of answer. Okay. So that's the idea there. And so to end this program, like every program needs to stop eventually, we have to tell it to exit. So let's do the exit system call. Remember that from last time? Let's go and steal that code from last time. Lecture 1, return in assembly this bit. So paste it here. And so in W0 goes the exit code, and here's a fun thing we can do. Let's put W4 in W0, because that's the value we want to look at, right? So move the value to exit with, to return into W0. It's always got to go there. And then the special code number that exits the program goes in X8. So 93 is the special number that goes in X8 to signify that, hey, we'd like to use the exit system call. We'll talk more about this later. Then SVC0 to say, all right, I set up my system call. I put the number in X8. I put the value I want to exit with in W0. Go and do that thing, please. So whatever this answer is, once I assemble and run, it should be placed as my exit code. All right, so let's see. Let's make it happen. So to run this program, we say AS for assemble, yeah, AS arithmetic1.s, and that will create an object code file. We can call it arithmetic1.o. So there it is. And then to make an executable file, you have to call the linker even if you only have one file. It just makes it executable. So arithmetic1.o, link it with nothing, essentially this time, and make an executable file called arithmetic1, please. So there's my final output that I can run with the /. So I hit that, echo, $? And apparently the answer is 56. Is that true? We can ask Python. Oh no, syntax error. Okay, so yeah, it is 56. Cool. So cool. That was our first taste of assembly. I like it. So all right, that was that. Please yell at me if you have any questions about this stuff. I'm happy to talk more about it on Discord and office hours, whatever you want. All right. So there are a bunch of other cool assembly instructions, and you can go to these pages, right? I gave you these pages. Go to them and look and see what there is. Like, you can go and look at the add instruction, for example. Like, what else can I do? There's a bunch of different kinds of add instructions. One that took that immediate value, one that took a normal register that you could maybe extend or shift. There's just a bunch of different things. Like, here's what add looks like. And you can optionally give a shift amount, which like does some bitwise twiddling as you're doing your add instructions. Pretty cool, all the things that you can do. Okay, so you've got plenty of options. Here are some cool other ones. If you're ever doing matrix multiplication, for example, you might need to multiply things and also add. So this is a fun one. It does them both. This is called multiply and accumulate. So it does x3 times x2 plus x1, and it stores it into x4. That's pretty cool. A lot of times when you're doing multiplication, remember that if you're multiplying two 3-digit numbers, the answer is going to be a 1, 2, 3. It's going to be like a 5. It could be 5 or 6 digits. It's going to have more digits than these. And the same is true in binary. So if you have a 32-bit number and you're multiplying a 32-bit number by a 32-bit number, the answer might be so big that it can't be stored as a 32-bit number. So this is called multiply and elongate. There's an extra L. It's a longer one. So it does your multiplication, and the answer, the full answer, is being placed in an X register where there's twice the room, where you won't overflow, which is really cool. Okay. And then sometimes you have like an int and a W register, but you want to do fancy things that require 64 bits. So you can extend. You can extend your W register, place it into some other X register, or the same one. So that extends a 32-bit number into a 64-bit number. And you don't have to do that if it's positive, but remember how negative numbers are stored? You might have to make a 1 in a lot of large places and a lot of high-numbered bits. Okay? So that's only necessary if you have or might have a negative value. And then one quirk of ARM assembly is there is no modulus operation. That just doesn't exist. There's no way to do like x0 mod 3 easily. You have to kind of split it up, and I'm going to force you to figure out how to do that. There's no instruction for that in assembly land. So how in the world does it work? We'll have to figure that out. Okay? So with that, we have this program now. I want to teach you how to use the debugger. It's called GDB. That's one kind of debugger. That's short for the GNU debugger. It's made by the people who make G++, the C++ compiler that we're going to use. So let's use GDB. And I'll show you how to like watch the register values change. You can print stuff out. It's really cool. Okay, so I'll walk you through all these different options. Okay, so we're going to use the GNU debugger here, and the way that you use it, all right. In order to use the debugger, let's see, what else do I want to say here? I think we're good there. So yeah, let's do the debugger. In order to use it, you have to compile or assemble if you're doing assembly stuff. Assemble on link, you have to put -G every time you do something. All right. So if we use the assembler AS, we have to use AS-G because that adds information about like where in the file we were, which is helpful for debugging things. So AS-G, LD-G makes it easy to use GDB. The program still works as normal. Like it's still there. But now we can load it into GDB. GDB is just another terminal program. Say GDB, name of the program. And so for us, we have a program called arithmetic1. We'll say GDB arithmetic1. And this plops us into GDB. It has a long spiel that it wants to give you at the start, so I didn't have enough room. So I'll type enter. And now I'm at the GDB prompt. All right? And it has my program loaded. It has the arithmetic1 program loaded into it. It's ready to run it, potentially. And so, if you would like to run the program, you just say R and hit enter. That's short for run. It's like, all right, ran the program, program's over now. So that's kind of not useful if you want to watch stuff happen. So instead of that, we can tell it to run the program after setting some things called breakpoints. So if you say B, that's short for breakpoint, you can say B space and give a line number. You say, hey, please stop the program on line whatever. So I'd like you to stop the program on line, let's say 3. That's the first line here of arithmetic1.s. So the way you say that is, all right, I have arithmetic1.s. You say the name of the file. I want to set a breakpoint on this file, colon, the line number I want to stop at. All right? So break arithmetic1.s:3, and that sets a breakpoint. And so if it ever gets here, it'll stop the program so you can like step through it, which is really nice. So now if I run the program, it'll ask me, do I want to rerun it? And yes, I do. You could have just started with this. So set the breakpoint before you start the program. And so now R for run, it stopped the program right here. Isn't that cool? Right before this is run. And so let me exit out of GDB. Q for quit. Why? Let's do that all over again. So let's break on a different line. Say break arithmetic1.s. Let's break on line, I don't know, line 4. Boop. Hit run. And so now it's breaking on line 4. It's right before it runs this code. So it's showing you the line there. It hasn't run it yet. It's run the one before, though. So if we looked at W0, and we can, it will tell us that 87 is in there. It will have placed it in there by then. All right. You can say P for print, and you give the register you want to look at with a $sign. So I'd like to print the value, please, of W0. Print $W0. And what do you know? 87's in there. And we haven't run this line yet, so there could be just garbage in W1. So let's print whatever's in W1. It's probably garbage. Okay, somehow it holds 0 right now, but it could have been anything. Okay, so that's the idea. So that's pretty cool. If you want to look at a bunch of registers at once, you can say info registers. And then it will show you every register. There's a lot there. It'll show you in hex. It'll show it to you in decimal. Type enter. There's a lot of registers here that you can look at. Like here's a bunch of things that shows you what PC holds. That's the address of my current instruction. Hoo-hoo. A lot of cool stuff. And then for short, you can do IR, I space R, short for info register. Same thing. That was pretty cool. So if you're happy, like you saw what you need, just want to continue the program, you say C to continue. We don't have any other breakpoints, so it will just run to completion. That's cool. And if you want to like stop and like go through lines one by one, you can say step or next. So let me show that to you. So let's quit out of GDB. I'll go right back in. One other thing I want to show you for breakpoints is you can give a line number or you can give a label. So I can say break whenever you get to the _start label. That's an easy thing to do. So like it'll break essentially on this line before it starts doing anything at all. So run. So now it's on line 3. That's an easy way to do it. You don't have to type the name of the file. So all right, I have this, and I like to watch it work. So I'd like to say, to run one line of your file, you can say step. Step. So it ran that thing. Now if I print W0, it holds 87. So now I'm on line 4. I can say step again. Print W5. I see that it holds, oh sorry, excuse me. W1 is what just got run. It was line 4 that run. We're on line 5, we haven't run it yet. My bad. So there it is. It holds 25. It's working. It's working. We can watch it work. That's really nice. All right. The difference between step and next is step potentially goes into functions, and next does not step into functions. It runs those to completions. Like go into the next line that is source, even if like we have to run a bunch of lines inside of some function somewhere. So that's that idea. Okay. So step and next. They work like that. Also, if you have a C++ program or also a C program, you can do step I or next I to run assembly rather than the code here. Like you might have C++ code really in the text, but I want to walk through what the assembly is doing and say step I or next I. Those are equivalent when we're running assembly programs. Okay. So next we're not calling any functions, so next is just going to go to the next line anyway. No big deal there. So yeah, you can watch things work. Say next or step. And then you can see what just happens. Like W2 just got a value. Should hold 7. And it does. So step. And if you just want to run the previous one all over again, you say enter. It'll just step it again. So this did the addition. W0 plus W1 just went into W6. What's in W6 right now? So you can watch everything work, and just if something goes wrong, you can figure out where it goes wrong by printing things out like this. Okay, that's cool. If you get lost, if you don't have Vim open in some other window, you get lost and you're not sure where you are right now, you want more context, you can say list. And that shows you some information about your line 10. It's going to show you some lines before and after. Kind of tell you where you are, which is nice. And yeah, you can also say disassemble if you're sitting in C++ code, at least. And it'll show you the corresponding assembly that that C++ code got translated into. Whee! It's like, all right, here we are right now. Here's some stuff before and here is some stuff after. Again, there's no difference because we're writing assembly. But if we were debugging a C program or a C++ program, and you can use GDB for those things, it'll show you the corresponding assembly that I got translated into, which is really nice. Okay, so there's all that, and yeah, so we can be like, all right, what is the value that's going to be printed out? Well, it's the value that's in W0. So let's get to line 15. Let's break on line 15, because then I will have the value that I care about looking at in W0. So let's set a breakpoint, arithmetic 1, on line 15. Let's continue until the end of the program or the next breakpoint. And so it gets to that new one, line 15. It's stopped. So it just ran this line. Print what's in W0. Oh, that was 56, and that was the right answer. So cool, we can continue debugging the problem. If there was a problem, it wasn't with that. Okay, so that's kind of the idea. That's GDB in a nutshell. Come back to this slide. There's so much. It just takes playing around to fully understand it. Okay, so that is the GNU debugger, and I think that is a good enough little start. All right, so let's see. What do I want to do? I have a question for you now. I gave you a program. Here is, let me give you this code. Dun, dun, dun. And you can go to the class code from last time to see the rest if you want to try it yourself and get like the exit stuff. But, oops, I did not want to do that. Here's all this. Switch this around, change stuff. Try to calculate this instead and store the result into W0, please. So write some assembly code to do that. I think that's a good exercise. All right, so let's try that. Let's do it together. Assuming you tried it yourself, let's do arithmetic 1, arithmetic 2 instead of 1. 2.s. So I'll steal all that stuff, and instead of all this, what we got to do is 4 times 7 divided by 3 plus 42. All right, so let's get those 4s and stuff in places. Let's do like move into W1, 4. Move into W2, 7. So now I got 4 and 7 to work with. I can multiply them, place them somewhere. So let's multiply into, let's say, W0, W1 and W2. All right, so now in W0 holds that multiplication. I want to take W0, divide it by 3. Okay, so I can move into W3, the number 3. And then I can, again, it's positive numbers, I can udiv into W0, W0 divided by W3. So that's going to take that answer in W0 divided by 3, place it back in W0. And then I want my answer in W0 still. So I want to add into it, right? So I want to add into W0 plus 42. I can either put that in a register. I can be like, all right, move into W1, the number 42, or I could use an immediate here. That also works for add instructions, at least. Definitely not going to work for division. For weird reasons, udiv. I couldn't have done something like this. I couldn't have done like number 3, sadly. I have to put everything in a register for division, at least. So udiv, for some weird reason, complicated reason, for some reason, can't take immediates. It's doing too many complicated things. Division is much harder to do than addition. That's why. That's the short answer, at least. So, but for add and sub, you can totally do this kind of thing. You don't have to put extra stuff in registers if you don't need to. And then, well, if I want to print the value as the exit code, well, W0 is where the exit code goes. It's already there. Just do the exiting. It's happy, yeah? So that's the secret there. So let me quit out of GDB. Let's see if this holds the answer, right? Let's see if it calculated the answer right. Let's do assemble arithmetic2.s -o arithmetic2.o. Let's link arithmetic2.o into just arithmetic2. Bam. Echo the return code. Apparently it's 51. Is that right? 14, 20, 28 over 3 plus 42. 42 integer division, that looks about right to me. Okay, that's the idea. So there's that. We did it. Pretty nice. All right. So hopefully you got that. Yell at me if you have any questions about that stuff. But let's keep on trucking. Let me show you how to put some global variables in your assembly program. So there's a special place called .data where those things can go. All right. So what if, like, we know that we have registers and we can put a bunch of stuff in registers, 31 things, right? That 32nd register only holds 0. What if we have more than those things that we want to hold on to? Well, then we have to use memory. So how do we talk to memory? Let me show you. All right. What you do is, one way to do it at least, is you can use global variables in your assembly programs. Global labels in the data section. All right. These words will make sense once I start using them. Okay. So when you make local variables, like in a C++ program, you declare them inside of a function. They go on the stack, and you can make stack variables by messing with the SP variable, because that controls where the stack is. We'll talk about that a lot more later, but we're going to use global variables instead because those are easier. All right, so let's talk about the data section. Let's make a program that uses this data section. All right, so if we have some data somewhere, we can load and store stuff to and from memory. All right, so this is short for load into a register, store from a register, and then we'll have to use move as well. Move moves things around. So that's kind of similar, but this is only inside of the CPU, only in the registers. Load and store for interacting with memory. Okay, so we know move, that's for moving stuff around within the registers itself inside the CPU. But if we ever want to go to memory, we can do it like this. All right. So if we have, and I'll show you this in just a second. If you have a place in memory, there's a label associated with it, like _start. That was a label. We can make other labels that have that are pointing to the start of like a number or a string. And so the assembler gives us a shorthand for that. We can load into x2 the address of where that label begins in memory. So that's one thing we can do with the load instruction. We can also, so like this takes this address and it stores it into, or let's say load, it loads it into x2. And then the other thing that load can do is if you use these brackets on a register, it goes to this register, because the register is meant to hold an address, it dereferences. The brackets are kind of like a dereference. It's doing this, all right? Dun, dun, dun. I'm going to dereference that thing at x2, go to the value at address x2, and read 64 bits of it, because that's how big x1 is, okay? So that stores 64 bits from this place, and every address in a 64-bit machine must be 64 bits, all right? Addresses are always 64 bits. That's very, very important. That's the reason registers are 64 bits wide. It's because addresses and registers go hand in hand inside of a CPU, okay? So every address must go in an X register, but you can read into an X register or a W register, honestly. Okay, so if you only wanted to, if you had just an int at this place, you had just an int, you could go there and just take an int's worth of data, place that into W1. That's possible. Okay, and then if you want to go in reverse, this is one of the few instructions that is not backwards because it's trying to be this similar to load. The store register instruction takes a value in a register and it stores it into this place. Okay, so it's doing this essentially in C++. It looks a little bit backwards, but it's trying to be kind of the mirror image of load. Okay, so that's a lot of words. Let's have an example of that. So let me take my arithmetic program to, instead of having values be immediate all the time, let's load some values from the data section, and also let's store the result in the data section as well. All right. And we'll look at that result with the exit code. We'll just make sure it's the same. Okay, so let me steal. I don't know. Do I want to do this one? Yeah, let's take this one, arithmetic 2, and we'll steal it into arithmetic 3, and I will make a new place down here. So outside of the code for the program itself, I'll start this data section. All right, so wherever I say .data, this is like the assembler knows this is the start of the data section. I can put global things, global memory down here that I can read anywhere. All right, so globals. go down here, and let's put some numbers down here. Let's, like, instead of this 4 being loaded immediate using the move instruction, let's load it using the load instruction, using the load instruction and the data section. Okay, let me show that to you. So let me put the number 4 here. So here's how you do it. You give the name of a label, like 4. This is where it starts, 4 colon, just like start colon. So just like this is another label. Like, all right, after this comes something important. So we're going to call it 4. That's its name now. And I like to hold the number 4 as an integer. All right, so this could have been as like a byte, as 32 bits, as 64 bits. To tell the assembler which one I care about, I say .word. That's the secret thing that means 32 bits. Word means 32 bits. It's a very complicated story. Just take my word for it right now. No pun intended. So .word means 32-bit. All right, means a 32-bit int goes here. Because it could have been 64-bit, right? So we're saying store just the 32 bits of 4. All right. You could have done a 64-bit number by saying quad. Quad means a 64-bit int. We only want 32, so we're going to store just the word there at the 4 label. All right. And then we also want to place the result in memory. So let's make a space in memory for the result. I'll call it result. There's the label. So this is where it begins. Go to here in memory. And let me just put an int's worth of data there. It can just be a dummy value right now, though. All right. So at the result label lives a 32-bit value that we can change. We'll eventually write to this with a store instruction. But initially, it's set to 0. Just making the space. All right. Could be anything. But we'll start off being 0. So, all right. So now for this 4, to use the 4, I'd like to load it. So I'll do this thing, the label, and then dereference the label. Okay. So it's easier to explain when I just do the code. All right. So in W1, I need to place a 4 eventually. That's what I was doing. All right. So I want to load the constant 4 into W1. So how can I do that? So first, I need to get the address of that 4. Where is this place in memory? Where is 4? Where is 4 the label? So to get there, I can say load. Load into, let's say, x0. Or no, let's do x1. Let's just talk with W1 and x1 today. And I say equals 4. So that goes to that. It finds the address of the label and places it into x1. That's what it's doing. All right. So that's essentially this in C++ land. x1 equals the address of 4. It's running that. And then I have the address of 4 sitting in x1. I'd like to dereference it and get the actual number 4 into W1. Okay. So again, it's another load. So load into W1 by dereferencing x1 and reading 32 bits from there on, okay, into this place. So this is saying W1 equals essentially star x1. And we just kind of overwrote x1 as well, so hopefully we don't ever dereference it again, because W1 and x1 are kind of the same place. So this will still work, though, the way we're doing it. So now W1 holds whatever was at address held in x1, which was 4's address. So now I dereferenced 4's address to get the actual number there, 4. Okay? So that's sitting there. And so now W1 does hold 4. It will work. Isn't that fun? And then I think what I also wanted to do, just to show you store, is let's store the result in the data section. Let's store x1. Or let's store into this result label. All right, so before we stop the program, and this exit syscall stops the program. So let's do our storing right here. Let's say, well, I need to place something in this place in memory, so I need to get its address. So where is the address of result? Let's store that somewhere. So let's load into, let's say, x1, the address of result. All right, so what this does, it sets x1 to the address of the result label, whatever is there in memory, and we can overwrite it by storing into that address. So let's store into x1 the value sitting in W0 right now. Okay, that's going to be our secret. So it's saying star x1 equals W0, storing that 32 bits at that address. And that's going to place in result the answer. And we're going to look at that soon in GDB. I'll show you how. But for now, let's just make sure that we get the same answer. let's do as arithmetic3.s dash o arithmetic3.o, and then ld arithmetic3.o into just arithmetic3. Oops, sorry, arithmetic3. That looks like the same answer to me. So cool, it's still working, and that's pretty nice. So we're using 4 from the data section now, from memory, rather than just an immediate value. So that's very important. That's pretty nice. Okay, so let's see what else. Yeah, if you wanted to, if you're ever working with characters, and eventually you will, you can, just like the number sign something, just like number sign 42, you can move number sign quotes A to move a character. Because what is a character but just a secret ASCII code number? Yeah, that's pretty cool. So that's another thing you can do. The next thing I want to show you before I show you, let's see. Yeah, eventually we're going to inspect this result place in memory. I want to show it to you. Maybe I can show it to you now, honestly. Let's try. I'll show it to you in GDB. So I want to load and assemble, sorry, link and assemble to my LDs. So I had arithmetic 3. Where was the AS for it? So dash G all over the place. Dash G, and just quickly, I'll show you in GDB arithmetic 3. And let's set a breakpoint after we've moved into this, after we've done the store, so on line 20, let's say. Set a breakpoint on line 20. Break arithmetic3.s line 20. And now let's run it. So it's stopped. And now let's inspect the value in the result label. Okay? So this is going to look really disgusting, but this is the way that I want to show you. So the result label lives at this address, address result. And then if I dereference that and tell the debugger that there's an int there, go and look at an int there, there's the answer. So it is being stored there, I swear. It does work. There are cleaner ways to do that, though. All right, so let's forget about that right now. Pretend that never happened. But yeah, let's move on and talk about constants. All right, so I'd like to tell you, like, how do you store constant values? Like, you've made those in C++ before, like const int x equals 42. Like, how did you, like, how is the compiler enforcing that fact? How does it make sure you never mess with this? All right, so in assembly, at least, a nice easy way to store a constant value, one that can never change, is to put the constant in the code part of the program. So the code section, which is separate from the data section, you can hold values that can change, right? They're global variables. But up here, this is, we didn't say it, but it's secretly called the text section. That's the place where the code lives. And the spot where the code lives in memory is read only for, that's like a good thing, right? Because if you didn't have that, you'd be able to change your program as it's running, change the instructions in memory. That's a little weird. We don't let that happen anymore. So you get a seg fault even if you try that. And the operating system makes sure you can never change code memory. And so if I put a .word 4 up here, that means that 4 really is a constant at that point. Like, it's never, if it's not part of the data section, it's part of the text section, it's part of the code, and it's just going to make sure that you never touch it. So let's take that 4 and let's put it up into the code section. So instead of here, boop, let's move it somewhere that we can't run it. Like, we're never going to get to this line, right? We're never going to get to and try to run this as code, because that's important. You never want to do that. But if I place this down here, we still have access to it. Like, we know its address and we can read it. We can't write to it now, which is awesome. So that this really is a constant now that's down here. It won't change anything about the program. This is really cool. So you can put constants down here in the code section. And you can try with the store instruction, get the seg fault, see it. The value can't be changed because you can't change code memory as the program is running. We've all just decided that that's a good thing, so we don't let that happen. That used to be possible, Programs used to change themselves as they were running. You can get some cool space savings if you do that, but that's well beyond the scope of this class. So yeah, if you have a variable that you would like to change, you put it in the data section. You want it to be global. But if you just have a constant, it's probably better to put it with the code, because then you enforce the fact that it can never change. So that's really cool. That's like the const at the assembly level. Okay, and let me just prove to you that that does not change anything at all. So we'll do an AS, we'll do an LD, we'll do a /, and we got our answer still. Cool. All right, so I have still swept so much under the rug. You guys, thank you for putting up with me so far. There's just so much random stuff I need to tell you as we're learning assembly and starting out. I still need to tell you what a system call is. It's like, all right, I'm asking the operating system to do something for me. That seems very magical. We need to make it not magical, okay? I also owe you, right? With every new language, we have to do a hello world program. I still haven't given that to you. So, like, they'd take my computer science card away if I didn't do that this lecture. So let's make that happen, all right? First of all, let's talk about this magical incantation down here, this SVC0. Let's move some fancy number into x8 stuff. That's called a system call, all right? So again, that's me asking the operating system, the Linux kernel in our case, to please do this special thing that only you have the power to do. Okay? So system call, syscall for short, it's just a special operating system level function call you can think of. All right? It's asking the operating system to do something that only it has the power to do, like talk to devices, to stop the current program, to tell me like what the current process ID of my current program is, to look at what time it is, stuff like that. Anything useful happens through a system call these days. It's just been done for you so far. Every system call has a number, a special number. 93 for some reason is what exit wound up being. And the system call, if you're doing one in 64-bit ARM assembly on Linux at least, it goes in x8. All right. The number of the syscall you want to run goes in x8, and then a lot of syscalls, exit included, take arguments, and those arguments go in x0, x1, x2 in that order if it takes certain arguments. So this isn't a good example anymore now, is it? If I go back to one where I actually put the value here, W0, that's the first argument for exits, the one and only exit argument. Okay, it's just the thing you want to exit with. If the argument is an int, and it is for exit at least, it goes in the W part of the corresponding register. So not x0, we're writing to W0. Okay? And then several syscalls return results. Exit, just by its nature, it's impossible for exit to give something back to you because the program will have ended by the time the system call runs. But if you did one that didn't stop the program, like a non-exit syscall, you'd still be trucking down here, and you'd have access to maybe a return value. And if the syscall gives you back an answer, it's going to put it in x0. Or if it's just an int, it'll give it to you in w0. Okay? So there's a big long list of syscalls. There's a page. You go to this page. You'll get this link when you look at the slides. But here they all are. And you can there are different numbers per different architecture. So if we want the ARM64 stuff, we'll click here to sort. And we can scroll down. Some syscalls don't exist on ARM64. But scrolling down to 93, you'll see that, hey, there's the exit syscall. It's right there. Let me zoom in a little bit. But there's 93. You can click on it, and it gives you more information on the exit syscall. It's like, all right, you think of it as a function, and it takes one argument. So that argument, if it's an int, it's going in W0. You start numbering up, okay? And then once you got it ready, you say SVC number 0. That's just the fancy way of saying, all right, hey, kernel, this is how you talk to the kernel. You say, all right, I'm ready. I'm ready to run my syscall. Do it. That's how it works. Okay? So, yeah, with that, let me show you Hello World. Because in addition to there being an exit syscall, there is a write syscall. It's way over here. It's called write. You got read and write. So write will write text, potentially. It'll write data to a place. And we can tell it to write to the terminal. All right? So here I am finally following through and giving you a Hello World program in assembly. So what we'd like to do is print Hello World to the screen, and the way we're going to get at that, this is actually what happens when you see out, by the way, is we're going to use the write syscall number 64, and we're going to write to a special file, because what write does is it writes to a file, all right? File descriptor, really. It takes a few arguments. It gives something back, actually, if you want to look at it. But it's going to write to a secret file that corresponds to the terminal output. All right. So secretly, this is a nice thing about Linux. At the beginning of every program, when your programs start, the operating system gives your program 3 special secret files that aren't really files. All right. It gives you standard in, which is your input. It's like a file that represents the input from the keyboard, that like your cin stuff that the user's giving you. It gives you standard output. It's a special file that you can write to. If you write to it, it writes to the terminal screen. And then it also gives you a third one called standard error, which is your error output. And these files correspond to numbers. File number 0 is your input, standard in. File number 1 is standard out, terminal screen, normal output. And file number 2 is your error output. It's like a different place, all right? And so you can write to standard out and standard error, and you can read from standard in, and then that, like, it's not a real file. It makes cool, fancy stuff happen on the terminal, thanks to Linux, thanks to the operating system doing that for us, all right? So let me prove to you, actually, that standard out and standard error are 2 separate things before we even get into the right syscall. It's like, it's worth your time, okay? So let me make a C++ file for once called standarderror.cpp. I'll prove to you that's a different place. So if I say cout hello from standard out, new line, that's that. That's cout. That prints to the normal standard output. You also have a cerr. Have you seen that before? Maybe it's been a while. So this is hello from standard error. If you write to cerr, it's really going to write to the standard error output, and they're 2 separate places. So if I, oh gosh, I just really messed that up, didn't I? Here, I don't actually know how to fix that. Let me, let's go to, in here, vim, or assembly, standard error, .cpp, there we go. Let's g++ that, standard error, -o, standard error. If I run it, we don't actually see any difference in output. It looks to us like, oh, it's just the same standard output both times. But really, there is a difference. And the difference happens when you try to like redirect the output. All right, that's the secret. So if I did something like this, if I said /standard error, let's write the output of that to like some output file.txt. Do you see how I get output still? What this does is it writes the standard output text to out.txt, but every standard error thing gets retained in the terminal because it thinks like, oh, that's not actually something you wanted. So here is only the standard out stuff in out.txt, whereas the error stuff is still there. All right, so that's the best example I can give you of that. So they are 2 separate places, which is cool. And now we're ready. All right, so file number 1. We want to write to file number 1 rather than file number 2. That's all I'm getting at here. So write, again, is syscall number 64. Syscall number 64. And what you do when you run the write syscall is you give it the file you want to write to in w something, because it's an int. So we're going to put the number 1 in w0. That's where your first argument goes, all right? And then we're going to give it the address of the string that we want to write out, and we're going to make a string in memory with this kind of thing in the data section. I'll show you that soon. We're going to place the address of that string. That's going to go in an X register, right, because we have an address. Address is in a 64-bit machine, must be 64 bits long. And then in X2, because it's a very large number, size t is a 64-bit number, then we give how many bytes we want to write. So it will read this many bytes from this place, that many things from here, and write to this file associated with that number. All right, so we're going to write to standard out. Again, that was a lot of words. It's easier to see this happen in an actual program. So let's do it. Let's do hello world.s. Finally, we made it. Let me take this. Yeah, let's do hello world.s. So I'll just steal all this stuff, and then most of this I don't need anymore. I still need to stop the program with return 0, so let's do like a exit 0. Dun, dun, dun. Move number 0. And then above this, I'd like to print hello world. And here's how I do it. All right, I'm going to say these things. I want to eventually call the syscall that's called write, and that's syscall number 64 that goes in x8. So move into x8, the number 64, and this is all part of printing hello world. Let's print hello world to standard out. Okay. Actually, let's include a new line as well. So, all right, I would like to be printing to file number 1. That goes in W0. That's the first argument of write. So which file you want to write to? I want to write to file number 1. That's standard output. So I'll move into W0 number 1. All right, so this is write syscall is number 64. And then we have file number 1 is standard out. And then I need to give the address in X1 of the string that I want to print. All right. And so in the data section, here's what I'll do. I'll make a place that holds the string. Here's how you make a string in assembly. So I'll say, got to make a label for it. So I'll say hello underscore string. That's the label where it begins. And to make a string in assembly, you say you say dot ASCII. And then between quotes, you put your string. Say hello, comma, space, world, and then a new line. So now that has placed, starting at this label, the bytes that correspond to this string. That's pretty cool. And so that's what goes in the next argument to the write syscall. In X1 goes the address. It's got to be a load, right? Load into X1 the address hello string. All right, so that's the address of string. Goes in X1. And then, we're still not done, then the last thing, X2, the last argument to the write syscall is how many bytes, starting at this address, we want to write to that file, to that special file. And all right, every character is a byte in ASCII land, so let's see. I have, my Vim shows me how many, \n is 1 character, so that's 14. It's really 14 characters, right? So 14 bytes I want to write. So move into X2. It's a 64-bit number. 14 bytes, please. So that's the number of characters to print from the string at the starting address given in X1. So this is disgusting, I know, but this is the nitty-gritty that we have to understand now. All right, and then we've set up the syscall. Now we have to say, go and do it, please. SVC number 0. Supervisor call. Run that syscall, please. Linux kernel. Run the syscall. I just set up, and bam, there is our program. All right, it's a lot, but it's going to do it. So if we do AS for hello world, -o hello world.o, LD hello world.o, into hello world. If I didn't mess up, drumroll please, I finally gave you hello world in assembly, guys. We did it. So I know that was a lot. You'll get used to it, I promise. But it's just a lot of stuff that I have to throw at you at the start, because this is the nitty-gritty details that you cannot avoid when you're working with assembly. All right? So, all right, let's continue. Let's talk about GDB some more. Let's talk about memory. If we want to look at memory in assembly, or just when we're debugging, even a C++ program, there is an X command, just like R for run, P for print. There's an X for examine in GDB. And it's going to show you the contents of memory starting at a certain address. So let me give you an example of that somewhere. Let's say I add to my standard error program the following. Oops. Just let's keep it in C++ for now. Let me go to my standard error program, and then I'll make some arrays. So let's make like an array of characters, different types to show different things. There's an array of characters, and let's make an array of ints. So this is places in memory that we can look at, right, that have addresses. That's where I'm going at. So G++ -G, standard error, output to standard error, and then I can GDB into standard error. All right. So I'm at my little GDB prompt. Let's stop the program on like line 8 where these arrays have been made. So let's break on standard error.cvp. on line 8, and I'll run until then. So that has populated R and R2. Those are just addresses, right? What's R? It's just oh, it's being fancy about it, sorry. So print, let's do R2. Oh man, GDB is just so cool. Really, you know that it's something like that. It's the address of where it starts. So, all right, if you have an address of where something starts, you can say X and look at that thing there. And X can take some special extra stuff. So if I just say X right now, let's see what happens. If I say X, like R, like it's gonna do some weird stuff. It's like it's gonna go to the address of R where it begins, and like the ABC, they're secretly here, probably, but it's not showing them to me. Okay, so it's actually there. It's like backwards. It's really interesting. So there's the ABC. It is 61, 62, 63 in hex, but we can see it in a clearer way. So here's kind of what you want to do. You say X/, and then you can give 3 things. The n thing is like a number. That's how many things you want to examine successively. So like by default it's 1. You can say I want to examine 3 characters, for example. And then you can say what kind of thing. Like, all right, 3, and then if I want characters, I say C, 3C, X/3C. For characters, give me hexadecimal ints, give me decimal ints, show me binary, T for binary, A for address, I for instruction even, it can disassemble, that's fine. And then U is how wide the thing was. So like, show me decimal, but interpret the things you see as a bunch of bytes, as a bunch of ints, so W, 4 bytes long each, 64-bit things, G. So for example, you can do something like this. Examine 10 characters starting at this place. X/10CR. And you see that, like, all right, there's A, there's B, there's C, and then in memory after that is some garbage. And there might even be R2 that bleeds into that. But you see, you should have just said 3C, essentially. That's kind of what's going on there. All right, so there's that. You can also examine 10 instructions, like main. Main is a label, secretly. Like, examine 10 instructions starting at the place called main. And that's the disassembly for main. Isn't that interesting? And it's not going to show them all to me right now because I don't have enough in my window. But like here's the start of the main function in assembly. Examine it, interpret the bytes you see as instructions. Main is just an address, which is funny to think about. But yeah, that's useful, examining memory. Okay. And I think the last thing I want to show you here in this little section is how to use a bunch of assembly files. So eventually you're going to write a bunch of code and you're going to want to get rid of it from like just one file. You're going to want to separate things logically. So let me show you. Let's take our hello world program and let's split it up. Let's split it up into the hello world printing and then like the exiting, because exiting is like everybody does exit. Okay, so what we'll do is we'll make a label just for the exiting. All right, and we'll use a new instruction. It's called branch always, b.al. All right, you can also use just b for branch, and it jumps you somewhere else. All right, so we're going to make some global labels, just like we had a global start, and we're going to branch always to another label. All right, and I'll put the exit code in a different place. So this will make sense again with an example. So I'll make an exit.s assembly file, and I'll place code for exiting here. So like I'll take all this code that I had in hello world.s and I'll move it to the exit.s file. So back to here. So I'll place it here. Add a certain label though. So I'll call this like exit label. This code here starting at this label exits the program. And because I have separate files, I want everybody to be able to see this. I've got to mark it as global. Global exit label. So now everybody can see it. So now people in other files can use this label. So that's nice. So there's exit label. You got all these things. And now I can tell the program to jump there. Jump to exit label, please. So I got all these things here. So I can say b.al, exit label. And b.al again stands for branch always. So it jumps your code to wherever that label was. So now, oops, I've got a couple files that I'm working on right now. So I got this one, and I've got exit.s. Let me assemble them together. Assemble hello world by itself into a .o file. Assemble exit.s by itself, exit.o. And now I can link them together. Finally, we're going to use the linker for its job that it's really meant to do. So let's link hello world.o and exit.o into a final program called just hello world. And so it's brought both of these things together. It knows where everything is, and I can run it just the same. And once it gets here, it jumps to exit label and starts running these lines, and that's going to eventually stop the program. That's pretty nice. All right, so it's all coming together slowly but surely, and yeah, that is exiting in a different place using multiple assembly files. All right, so yeah, let's keep on trucking. I know this is a bit of a longer lecture today, but I swear it's worth it, promise you. So let's talk about the difference between C and C++ before we go, and that'll be it. All right, no more making your brain heavy, any heavier than it already feels. All right, so Dennis Ritchie, very cool guy. He invented the C language, grandfather of C++. So let's learn about that original language that like started the whole craze. I will teach that to you now, just a little bit. So let's do hello world in the C language. And instead of .cpp, it's .c everywhere, okay? So if you were going to print stuff in C, there is no C out for you. That was an IO stream. That's a C++ header. It's standard IO for C. So we have those here. The C library, we say C standard IO in C++, but if you were in C, you'd include the header, and it's called standard IO.h there. Standard IO.h. That's apparently a tongue twister for me. And so instead of C out, if you want to print something, you got to say printf. Printf. And it says it's formatted printing. You give a format string and some optional arguments afterwards that tell you how to print stuff. All right, so yeah, we're going to do that. And then we're going to compile not with G++, because that's for C++ programs. We're going to compile with GCC, the GNU C compiler. That's what it stands for. All right, so this is probably the most famous language in the world. The Linux kernel is written in C. Like this, you need to learn C, and it's very low level. It's nice. It's just the start of everything. So let's do a hello.c file, and it's pretty much the same. You still got a main function. You still return 0 at the end. Instead of IO stream, you say include standard IO. There's no such thing as a namespace. So it looks like this, and to print hello world, you're going to say printf. Printf. And then you give a format string. That's what it's called. It's a string with formatting, potentially. And so I want to say hello, space world, and then a new line. And that's my C program. GCC to compile it, hello.c into hello. Bam. That's the start of everything. Oh, I'm so sorry. It's not standard IO in quotes. Somehow that got default included for me anyway. But it's those kind of it's the angle brackets. Excuse me, that was disgusting. Standard IO.h, as usual. So there we go. All right, I had quotes on the brain apparently. But apparently it's included by default for you anyway, which is hilarious. So, okay. If you would like to print non-strings, it gets a little weird. Printf takes format specifiers in the first string. If you give a %sign, and then you give some extra stuff after a %sign, it tells you what you'd like to print. %d, for example, prints a decimal integer that could be negative. It's a signed one. %f, for example, prints a floating point number. Stuff like that. So %c prints a character. You can do a lot of stuff. %s prints another string if you want it to be weird like that. But let me show that to you. So like if you have an int and you want to print the value of that int x equals 42, there's no C out anymore. You gotta use printf, and you gotta give a string as the first thing, and it's a format string. You say, all right, I want to print x, and the value of x, you say %d, and then like a new line. And this %d will be replaced with whatever you provide after. So like it goes in order. the thing that gets replaced with the %d, interpreted as an integer, will be x. That's kind of how you pass along things. And so like you give what you want printed with some placeholders. And then you start giving all the things you want to print. And to have fill in those placeholders. That's how format strings work. And so you see x colon space 42 new line. It does work. And it's a little weird. This is what our forefathers had to deal with. All right. So yeah, that's Hello World in C. It is the beginning of everything. All right. And that's where C++ came from. And honestly, we're going to prefer C in this class when we're talking about when we're operating between C and C++ in assembly, because C is just more sane, I would say. So let me show you the difference. Let's make a +1 function in both C and C++. All right, C and C++. It's going to get a little bit weird. All right, and we're going to generate the assembly for each of those. All right, so I'm going somewhere with this, I promise. So let's make a file called +1.c. Looks like this, just like it's what you would expect. Int +1, int x. It's like return x +1. It's a very simple function, but there it is. There's that one. And let's do the same thing in C++. So I'll make a new file, +1 cpp.cpp. Same code. Same code. But let's see if I can do this. So I've got the same thing a couple times. So I have +1.cpp, +1.c, same code. And then let's make the assembly out of both of those. We'll do G++ or GCC-S for +1.c. And we'll do G++-S to generate the assembly for the C++ version as well. cpp.cpp. And so that's created these files. We have +1.s that just got made and +1cpp.s that just got made. And, all right, this is where I was going with this. The +1 in C, +1.s, that's what this got translated into. And then the +1 in C++, +1cpp.s, that's this. And so here's +1, it starts here, +1 label. Instead of that in C++, instead of something sane, it's called _z5 +1i. Which do you prefer? So we just ran into what is called name mangling. All right, so the name, in C++ at least, of this function that we wrote, when it's being generated into assembly, it's having the types get placed next to it. So you can demangle it. There's a terminal command called C++ filt. And then we can give this thing. And it's like, all right, this is +1 and it takes an int. It's being encoded into the name of it. Whereas in C, it's just called +1. It's easy. But in C++, this is called name mangling. It includes the type of the arguments in the function itself. Crazy, all right? There's a reason C++ does that. Think about it. Here's my question for you. Can you do this in C? Can you have a +1 function that takes an int and returns an int, as well as a +1 function that takes a float and returns a float? You can totally do this in C++. Is this possible in C++? Or sorry, in C? Given what I just showed you? It's like, here's what +1 turns into, it turns into that. Here's what +1 over here turns into, it turns into that in C++. This is the C version. The answer is no way. Do you see why? Because if you did, this would have the +1 label, and this would also have the +1 label. You can't have two of the same label. So that's why it won't work. C++ gets around that by encoding, making a different label. It looks disgusting to us humans, but to the compiler, it's very nice. Okay, so there's that. And then I think that's pretty much what I wanted to say today. Do I want to talk about this next thing? We are kind of out of time. You'll read about this in the textbook anyway, but just briefly, like in C, there are no classes. C++ is the object-oriented one. There's only structs. Structs exist in C. You can put bunches of things together. There's just no there's no methods involved. All right. You do have to keep saying struct all over the place. It's a little bit different unless you use what's called a type def. So like you can make a struct point2d, for example, and then to make a point2d object, you have to say not just point2dp, you have to say struct point2dp. Which is kind of weird, but we'll see that later. All right. So that is our first real taste of assembly for the day. And that is where I want to stop. So thank you for getting through it with me. We did it. The final thing I want to show you is your first lab. I want to introduce your first lab, and I'll make a different video for that, for just the lab section time. All right, so I'll see you in the lab video, and that'll be that.